Welcome back, everyone. In this video, we're going to talk more about drawing Lewis structures, and specifically, we're going to talk about using formal charge of an atom within a Lewis structure to predict which Lewis structure would be the best or the most stable. Let's review for ourselves the rules for drawing Lewis structures. The first rule is to count up the number of valence electrons and account for extra or missing electrons due to the charge on the species. This rule is very often overlooked by students, and they tend to just count up in their head and not keep track of the numbers on paper as they're solving. This is a big oversight because it's easy to miscount and easy to forget to account for the charge. And so by writing down and showing your work for those numbers, it makes it a lot easier to verify that you've created the proper Lewis structure. The second step is to write out the atom symbols and connect the atoms with single bonds. In all cases, except for when hydrogen is the least electronegative, you're going to put the least electronegative element in the center. Let me state that again. The least electronegative element goes in the center of the molecule. And this is true for all cases except for hydrogen. Often, if you have a symmetric formula, that will suggest a symmetric structure. This comment here about oxyacids, we're not going to really get into for the moment, so we can ignore for now. It's also important to recognize that we want to start with just single bonds. Another common error that's made is that students will put double bonds or triple bonds on there before they need to. Third step, distribute the electrons as lone pairs to make complete octets. And then if you don't have enough electrons, that's when you start making a double bond or a triple bond as needed. If you have extra electrons, then after completing the octets, then you put them on the central atom. So let's now look at a specific Lewis structure. I'd like you to try this one, since we've already done Lewis structures before, and make your estimation as to which of these you think is best. So pause the video and try and evaluate this on your own. Welcome back. So how do we know if this is which Lewis structure is best? Well, a common way that we will have you evaluate is by looking just at the first step. You need to make sure you count up the valence electrons, and there should be 24 valence electrons. When you look at the number of electrons in each of these molecules, you should see that the one on the left has 26 valence electrons. Therefore, it is not phosgene. That's a very common distractor that we put into questions. And so by making sure that you follow the first step, you can quickly rule it out. But then how do we determine which is the best Lewis structure between B and C? They both have 24 valence electrons. They both have completed octets for their elements. So how do we tell? We're going to use formal charge to make the determination as to which Lewis structure is best. Formal charge is really just a bookkeeping method that describes where the charges are located in molecules. So for example, if we wanted to look at the OH, we're going to look at OH. We calculate the formal charge by looking at the number of valence electrons for a given element versus the number of electrons that are in the molecule. So if we look at the oxygen, then oxygen has 6 valence electrons. When it's bound in the OH molecule, we see that it has 6 lone pair electrons, but 2 of those electrons are held in bonds. And so it only gets to keep or count one of those 2 electrons when we're looking at formal charge. So the formal charge then of the oxygen is -1. If we wanted to calculate the formal charge of hydrogen, the number of valence electrons in the neutral hydrogen atom is 1. When looking at the structure, it has no lone pairs. and it has one electron that is, it has one bond, and so we count half of those electrons, and so that's a total of 1 electrons. So its formal charge would be 0. And when you look at this, the OH anion, we can see that the formal charges add up to be the charge on that molecule. Okay, so now let's calculate the formal charge for the 2 structures that were left over from phosgene. If we look at the number of valence electrons in the free neutral atom for chlorine in molecule labeled B, chlorine has 7 valence electrons. When we count up the lone pair electrons, that's 6. And then it has 2 electrons that are involved in a covalent bond. We count half of those. So its formal charge is 0. For the chlorine, the orange chlorine in C, since it's chlorine, it also has 7 valence electrons. But it only has 4 electrons that are counted as lone pairs. There are 4 total electrons in bonds, and so we count half of those. And so it would have a formal charge of +1. For the oxygen on the left, oxygen has 6 valence electrons. There are 2 sets of lone pairs, so a total of 4 lone pair electrons, and 2 bonds, and so half of those get counted, giving us a formal charge of 0. Then the oxygen on the right, oxygen always has 6 valence electrons. It has 6 lone pairs, or rather 6 electrons that are as lone pairs, and then only 1 covalent bond, so we count 1 electron there, and that gives us a formal charge of -1, which we indicate there with a negative charge near the oxygen. Now, let's talk about some things. Why did we not calculate the formal charge of the chlorine up top? Well, as you can see in both structures, it has the same bonding pattern, 3 lone pairs and 1 single bond. And so that's not what's changing between the 2 structures, so we don't need to evaluate the formal charge there. Rather, we need to evaluate the formal charge of the chlorines and oxygens because they appear to be different in the 2 structures. So now that we've calculated formal charge, how do we determine which of these structures is better? We're going to see that it comes down to the electronegativity of the elements that are involved. So the best Lewis structure is the one where formal charges are minimized. They're as close to 0 as possible for the greatest number of elements. However, if you have to have a positive or negative charge, you want the negative formal charge to go on the most electronegative element. The corollary to that is that positive charges go on the least electronegative element. And and therefore that means that the structure on the left is better. It has formal charges of 0 for the different elements. And as we noticed earlier, the sum of the formal charges is equal to the net charge on the species. And you can use that as a way to check your structure. So if you were to calculate the formal charge of all 4, you would see that the chlorine and the carbon in the middle both have a formal charge of 0. So by adding together the formal charge, we get a sum of 0 and a sum of 0, which is a good sign because phosgene is a neutral molecule. Now, do formal charges actually exist? Not really. As the name implies, they are formal. This is a formalism, a way of giving an approximation of what the charge would be, assuming that the electrons were shared fully equally between 2 covalently bound elements. But we know that in reality that there are bond dipoles, that there is an unequal sharing of electrons. Therefore, a molecule that has no formal charge or elements with no formal charge could actually have a charge depending on the difference in electronegativity. So formal charges are a good approximation, and it's a good way of accounting for where the charge could be, but it's not the best method. In chemical experiments, we can actually determine the real charges, and you could compute the actual charges by looking at the difference in electronegativities between the elements. All right, let's do a couple practice problems. I'd like you to pause the video and try this one on your own, and then I will walk you through it. Welcome back. So we want to know what's the formal charge on the nitrogen atom in nitrate. So this requires that you be able to draw the Lewis structure of nitrate first. So what do we do there? Hopefully the first thing that you did was count up the number of valence electrons, 24. There are 5 from nitrogen, 6 from each oxygen, and then 1 electron due to the charge. So that's a total of 24. Then we put the least electronegative element in the center, that's nitrogen, and you can determine that using periodic trends, and draw single bonds between the nitrogen and the oxygens. We then want to distribute the remaining electrons onto the exterior atoms as lone pairs in order to satisfy them. After we do this, we can see that all of the elements on the exterior are satisfied. However, look at nitrogen. Nitrogen only has 3 bonds, and so it can only claim 6 electrons. In order to make the nitrogen satisfied, we need to use a double bond. So we take and replace one of the lone pair electrons with a double bond between the oxygen that donated those electrons and then the nitrogen. Now, if we want to calculate the formal charge, the way that we do this is by comparing the number of electrons that an element has as a free atom versus the number of electrons it can claim in the Lewis structure. So the equation, if you will, that we looked at before was that the formal charge is equal to the number of valence electrons minus the number of lone pair electrons minus 1/2 of the electrons in bonds. And a way that you can really think about this is that we're making a comparison. We're comparing before and after. So before the element is in the molecule and then after it's in the molecule. And so we're looking at how many electrons did it have versus how many it has now. So let's do this process for the different elements. For the oxygen that is singly bonded, we notice that there are 2 of them. And because they have the same bonding pattern, they should have the same formal charge. There are 6 valence electrons in oxygen. Each oxygen has 6 lone pair electrons, and each electron has 2 electrons in the bonds. Thus, we have a formal charge of -1. Another way you can think about this is that we started with 6 valence electrons. In this molecule, we have 7 valence electrons that oxygen gets to claim. Therefore, it has gained 1 electron. 1 electron has a charge of -1. For the doubly bonded oxygen, it has 6 valence electrons, 4 lone pair electrons, and then it gets to count half of the electrons in the bonds, so that is 2, leaving it with a formal charge of 0. Nitrogen has 5 valence electrons, no lone pairs, and it gets to count 4 of the electrons in those covalent bonds, giving it a formal charge of +1. we should be able to add up the formal charges, -1, -1, +1, to get an overall charge of -1, which is the charge of our species. Here's one more question. Go ahead and try this one on your own, and then come back and I will help you to figure it out. Welcome back. So we want to know for which of the following structures, which of the following is best for carbon monoxide? And I've omitted the formal charges in the answer choices. So to determine which are the best, we need to evaluate in two ways. One, count up your valence electrons. Make sure that they are accurately representing the number of valence electrons. So by looking at the number of valence electrons that we should have, which is 10, we can see that the molecule A, this has a total of 2, 4, 6, 8, 10, 12, 14 valence electrons. B has 2, 4, 6, 8, 10 electrons. C has 2, 4, 6, 8, 10, 12 electrons. And D has 2, 4, 6, 8, 10 electrons. So we can immediately rule out A and C. Now we draw the bond between carbon and oxygen, starting with a single bond. Then put on the lone pairs of electrons to try and satisfy the elements. Notice that we can't do it. We don't have enough electrons. So at this point, we start drawing multiple bonds. Start by drawing just a double bond. And notice that we have donated two of the electrons from carbon, so it's sharing with oxygen. Are the elements satisfied? Not yet. Oxygen still only gets to claim counting 6 electrons, so it needs to have another bond. At this point, we reevaluate. Do we have 10 electrons shown? Yes. Do both elements have their satisfied octet? Yes. Now we calculate the formal charge. For carbon, it has 4 valence electrons. It has 2 electrons in lone pairs, and then we subtract this half the electrons in bonds, giving us a formal charge of -1. For oxygen, it has 6 valence electrons. It has 2 lone pair electrons and 3 that we count from the bonds, so it has a formal charge of +1. So those are our formal charges. They should add up to be the charge on the molecule, which is 0, and they do. Remember, formal charges are just an accounting tool. It does not describe the actual charges. If we were to predict them, we would actually think that the oxygen would be partially negative and the carbon would be partially positive due to the differences in electronegativity between them. That's it for this video. Thanks for watching. Have a great day.